Shared memory is a way for multiple processes to communicate and share data efficiently. And this is said to be one of the fastest ways for processes to communicate. Now, I'll be introducing and sharing rather one program written in C language. And we will be seeing its demonstration on Linux platform, where what I'll be doing is from the parent process, I'll be creating a specific region of memory, okay, which would be used by other child process to get the data. So in general, one can say that processes are sharing a specific region of memory to exchange information. Now to introduce this code, I would be using some important system calls which I have used in this particular program. First is Shmget. Right. So if I write, this is for creating a shared memory area. Okay, this function call or this system call is used for creating a shared memory, Shmget. Now, suppose if a parent creates shared memory area, we have to attach that with parent as well as child. Okay, so for that purpose, we have to use another system called SHM attach, SHMAT. Correct. So if we see SHMAT attaches memory segment identified by SHM ID, and we are going to make use of this, like this is a prototype of that function SHMAT. Now, what I'll be doing is in parent process, when shared memory area is created, okay, then it is attached. I would be reading one value which I'll be sharing here by attaching that area by passing the address. So let us say I have given name of that variable to be shared memory or shared mem. So I will be reading input value for that particular variable, which would be accessible in both the processes, in parent as well as child. Now in child process, what I'm going to do is I am going to use that shared memory value. Okay, and I will be printing square of it in the child. Whereas in parent, it will remain same. Fine, like whatever the value that you input, both cases, like in child as well as in parent process, you would be seeing that same value would be there. But we just will be printing in the child. Now, after this processing is done, like shared memory is created, then shared memory is attached, then value is processed from child. Further, like after the work is done, that memory area should be detached. So we would be using one other system called SHMDT. So SHMDT would be only just you have to pass that memory area address, which is to be detached. This is used for detaching, correct? Shared memory detached. So if I go up and if we try to see SHMDT function, SHMDT detach the shared memory segment located at the address. Fine. And once the memory area is detached from both the processes, we have to remove that shared memory area. Now, this is not necessary. This can be considered as an optional, but it is better rather you remove that memory area. So to do so, we have to use a system called man shmctl. So this would be used for removing that memory area. Fine. Now, like what are the advantages of using shared memory? No need for context switching like pipes or message queues, which would be talking later. It is efficient. No need to copy data multiple times. Again, it is said to be one of the easiest way for inter-process communication. So let us see the code. So let me open that code. I have written this code specifically to introduce this shared memory area and for this course. So initially, if you see at the start of the program, I have added some header files. These header files would be providing functions for standard IO, process handling, shared memory management, and so on. Now, as I stated about shared memory system calls, along with that, I would be using two, three other system calls like fork for creating a child process. Then we are going to make use of, say, wait. So, for example, if I see wait, wait the process to change the state because child would be processing some data. We want parent to wait for a child to finish. That's why we would be using this wait system call. Further, I'm going to make use of function sleep for adding just a delay. Like this is the function sleep for specified number of seconds. So it will wait for that much amount of time. Okay, so here, as I stated, these are the header files, okay, which are added by us uh, to get information about, or maybe to give references or prototypes for standard IO functions, process handling function, and shared memory management functions. Here, I have declared one variable called SHMID, where we will be getting ID of that particular variable, and we will be creating a memory area which would be referred as shared memory, shared underscore memory. Now, let us fire a shared memory segment creation function, shmget. Now, you will see that I have used some parameters as per the standard prototype. IPC private flag, this would be ensuring that a new segment is created. Then we are creating it for integer size. So that's why. So we are providing what should be size of it. And then this IPC create would be for creating. And you will see like this memory area which we want to create, it will be available as a read as well as with write permission. That's why 0666 is added as a value there. So what are the memory area that is created? The number which is returned there by the appropriate function. So if you write shm get, it returns an identifier of the memory segment. So shmid would be creating an identifier shmid. Fine. Now, what I'll be doing is I am giving call to the fork system call. So we know that like when fork returns 0, that means would be executing in child. So I have divided my code into two parts. First part is say for a child process and other part is for parent process. Now let us first initiate from the parent process. We will address parent process. So what we will do is whatever the shared memory is there, we will attach it with that ID. Okay, that memory area would be attached with the shared memory. Now we will print statement like enter a number, and we will read one value for that shared memory area. And now here what I did is I printed that value from parent, what value I see. Now, as I have already initiated as a parent child process creation, I want that child to finish its execution. That's why I would be waiting. And when child finishes, this next statement would be executed. And then later this one. So let us go first to the child process. Now, child process will sleep for a while. Like we'll ask child process to wait for a while because in parent process, we are going to read the value and we are assuming that there will be 10 seconds required for user to input that number. That's why we have added sleep 10. Now we will attach the same memory area which was identified by SHMID with the child process. So shared memory is read there. Now it will print from child what value it read from that shared memory area. So like if I input 6, then 6 would be printed here. Now in other case, like we wanted to display a square, that's why we'll display that square here. And once it is done, the printing is done, we will detach that memory area from child. Now let us assume that child finishes execution. It will come back here because it was waiting for that child to finish. Now it will print this from parent. Before detaching from parent, what is the value? So it will display the same value because we haven't written back the square with the shared memory. That is the reason. Correct. So then we will detach it and then we will remove that shared memory area. And this is how the code would be working. Right? So let us close this. Let us write gcc-m32 shared memory.c. Fine. So let us execute this. Now I want to show you like what happens like if pro, program starts, we want to see that the processes are created. That's why I would be using ps command with the state to be displayed. So aux, and we will grep a dot out from there, from the memory. Fine. So like right now, if I fire this, it would be showing only grep thing because we haven't executed yet. Fine. Let us execute. So once we execute, now you will see this. Now, as we are not inputting any value, child was waiting for 10 seconds. So when its wait is over, probably you will see that child process entered into defunct function, defunct process, because it displayed. It was trying to read the value. It never got value. So that's why it is assigning value 0 to it and it printed it there. And one may see here that our child process entered into zombie state because it was waiting for parent to give the value. Nothing was displayed. So it removed, but it could not leave the memory space, address space, because parent was still executing. And we know that in parent, we have a scanf statement. So when I input scanf like a value for that shared memory, it will display only that value because child already finished its execution. Now you will see here now, both the process were terminated. Now we know that the child is waiting for that amount of time. Okay. So let us again execute this. Dot slash a dot out. Let me give here value 4. Now parent is having 4 value. Now you will see the child is not showing Z because child was reading the process. It was waiting for 10 minutes, sorry, 10 seconds because we provided sleep 10. Now you will see in child, it was reading the value from the shared memory. Okay, it displayed the square, finished execution. And then later came back to parent. Now parent saw that child finished. That's why parent is printing from parent before detach 4. It printed this, it detached it, and then removed the memory area. And then program execution was successful. Let us execute one more time. Let me type 7. It is waiting for 10 seconds. You can see like what happened. Correct. The process was working on IO only, both the processes. That's why they never entered into Z plus. But if I go here and if I don't input anything here for the parent, so it will wait for 10 seconds. And once it is done, you will see that it will enter into Z plus with defunct state. Now you might have identified, I haven't inputted any value here. That's why child process was waited, then it could not find any value. That's why it terminated. Terminated in the sense entered into zombie state. Fine. That's how this program works.